We start off with the gripper test. Here we can see how the P control correctly moves the pincers together to grab the marshmallow. The arm then contracts and the pincers move apart to drop the marshmallow into the chute. Now we take a look at the trajectories of the robot arm. The gripper portion of the simulation was done separately to simplify it. The arm takes the first marshmallow, retracts, and drops. Then the arm repeats this process for the preceding two marshmallows. Here is a list of our satisfied requirements, constraints, and goals, with a brief justification of why we believe they are satisfied, as well as some interesting technical details. Here are our unsatisfied goals. The main area of weakness is the high cost and power consumption of our electrical components. And now the feature demo. First, we look at the PCB. It was made with a minimum amount of vias. We used M3 holes for mounting the board to the housing. The ground pins are easily visible on the bottom copper layer of the circuit, and it has a compact design that resembles multi-sim circuits for better debugging.
Next, we want to showcase our dynamic vector input system in Simulink. We used a switch block that was conditioned on timing constraints. In this video, the switch will be turned on to the upwards position when this timing constraint is met at 0.5 seconds. Before that, it will be reading the bottom value of step input -1. We use the same mechanism to create our unique and dynamic vector input system in Simulink for our demo. Here the red arrow indicates the flow of the value that was read. Like before, we read the bottommost value, for both timing constraints are not met yet. The first input vector angle we fed into the motors led it to grab well number 1. After the position is assumed to be settled, the time constraint, we grab another value from the bottom here that leads the motors to a position where it is above the garbage can and it could drop the marshmallow. After settling there, we feed it the angle vector that leads the motors back to the origin.
Let's start off with the gripper. Here we have a 1 to 25 torque reduction. You can see how when one rotates, the rest rotate with it. Here we look inside the gears. We have a ball bearing inside the lower gear to reduce friction. Additionally, the pincers are being secured with a screw. In between the screw and the gear is a standoff, and to reduce friction, washers have been added. You can see that at the bottom, the motor is secured with a clamp. You can see here the ball bearings for the wrist motor, as well as the standoffs used to secure them and the gears. The same thing for the elbow motor and the shoulder motor. Another detail here is that rather than using a heavy metal nut, the M2 screw for the wrist clamp takes advantage of the shape of the forearm. Here's the movement of the entire arm. And here's a close-up of the shoulder motor's gears. Here we have the breakdown of the costs of each item. The total cost of the design is $2,300. One area this could be improved is if more of the same kind of component was used. For instance, there are multiple M2 nuts and screws, but some are only used once, and these McMaster components come in sets of 50 or 100. Regardless, this is a very low cost given the nature of this project, and so the low budget goal has been reached.